Okay, so welcome everyone to the next session. So I guess we can get started. So this is the PhD Symposium 2, and the first speaker will be Messe Delaunay from UESTC, and the topic is Spark Performance Optimization Analysis in Memory Management with Deploy Mode in Standalone Cluster Computing. So Messe, you can get started. Can you play the video?
Hello, welcome to my presentation. My name is MESSI from USTC, China. My paper entitled with Spark Performance Optimization Analysis in Memory Management with Deployment Mode in Standalone Cluster Computing. When we see introduction part, Spark is actually one of the big data analytics tools which is recently designed and used memory computing, especially to improve efficiency of data computing by minimizing discrete which actually also minimizes data load latency. Spark is actually a good fault tolerance and supports a distributed computing framework. It is actually also designed based on the principle of Hadoop MapReduce algorithm or framework, which is actually more suitable for interactive application, especially it is used for both batch and real time. It also has almost more than 180 parameters which helps to optimize its performance according to user requirement. Its performance is depend on combination of those configuration parameter value. Based on this, our experimental actually focus on memory management and other parameter, especially deployment mode with other parameter to investigate whether it is improved performance of the application or not. When we come to experimental methodology, to do our experiment, we also identify different experimental approach, tools, component, deployment approach, methods, parameter configuration as experimental criteria based on our experimental goal. Based on this, we identify a Spark standalone cluster deployment model as best deployment approach and the methods, together with experimental variable and parameter configuration along with their deployment model. Spark standalone cluster component interaction were also identified as driver, master, cluster manager, and executors. Executors are actually run in workers. So experimental model is designed as an architectural model to show its component interaction. Application interaction anatomy was also identified and designed as one of application interaction model that computes tasks. Based on this, different Spark workload were identified, developed, and used for evaluating performance under different deployment mode and parameter. Okay, when we come to experimental setup is normally categorized into environmental setup and configuration setup. When we say environmental setup, it is hardware and software parts. Especially software is a software that actually used for our experiment, which is actually allowed to do our experiment, maybe by writing and executing and different way it allow to do our experiment. When we move to configuration setup, it is a setup that allow to perform our experiment. So it was actually categorized under different category along with their parameter value, which has actually its own default value and the new value. So parameters are their own default value as well as their new value that actually used for our experiment. Okay, when we come to the procedure to do our experiment, we first install and configure different software according to our experimental model. Once installation is completed, we try to develop different Spark application using Scala programming language, and then finally we create jar file for each application. Once jar file is created, we try to form a Spark cluster by starting one masters with two workers, so that we interconnect those workers to masters via master URL. Finally, we submit different Spark jar as a Spark job to cluster with different parameter value and different deployment mode to measure performance of Spark related to those configuration. At the end, we look for experimental results. So experimental results show different performance rates for different workloads under different deployment mode and parameter value. So the result is visualized in different workload with different deployment mode and parameter value. Okay, performance result in changing parameter value. Performance improvement comparison between default and the new value is normally considered by taking deployment mode as a base reference. So the result is show performance in new value configuration is better than a default parameter value under both deployment mode in all workload. This means increasing default configuration parameter will increase performance of Spark under both deploy mode in all workload, as it's already shown in figure. Okay, when we see performance result in deployment mode, so results show in submitting job in cluster deployment mode has high performance than submitting job in cluster deployment mode in case of word count and page rank. However, in TerraSort, the reverse is true, which means client deployment mode has high performance than in cluster deployment mode. This implies performance in deployment mode depend on type of application rather than value, or which means it is directly related to internal structure of application. Okay, as a conclusion, Spark is one of high-speed big data analytics tools which use memory computing. Some of its parameter is selected to further optimize its performance based on our requirement. So once we did our experiment, we get a result, which means increasing default value of the number of executors per worker, number of core per executors memory fraction, increase Spark application performance under all deployment modes and workloads. At the end, deployment mode does not determine Spark performance, rather than Spark performance actually depend on type of application or internal structure of application, which means Spark performance does not depend on deployment mode. Okay, thank you for your time and attention. Welcome for any question.
Okay, thank you. So are there any questions by the audience? So I had a quick question actually. So you mentioned that the performance depends on the application, right? So what are the characteristics of the application that basically determine the performance with the different modes on Spark? Can you hear us, Messi? Maybe you're having some problem with your microphone. Can the others hear in the audience? Can the others hear what Messi is saying? Maybe in the interest of time, we can probably Messi can just maybe answer the question in the chat, but we can probably move on to the next next presentation. So the next presentation is by Yifan Q by Rensselaer Polytechnic Institute. And the topic is design of database systems with DRAM-only heterogeneous memory architecture.
Hi, everyone. My name is Yifan Chao. I'm from Rensselaer Polytechnic Institute. It's my great honor to present my research in SD PhD forum. So we all know that memory plays a very critical role in computing systems, especially database. As a cornerstone of modern information technology infrastructure, database relies on the deployment of a large amount of memory in order to achieve high performance. As a result, memory heavily influences the performance and cost of database systems. Over the past few decades, the semiconductor industry has been actively searching for new memory technologies that could be better and cheaper than existing DRAM technology. So practically, variable memory technology must meet strict constraints from many aspects, including cost, reliability, latency, bandwidth, and endurance. So after 20 years of intensive research, Intel's 3DXP Optim DIMM is the only new memory technology that can be deployed in computers. However, compared with DRAM, 3DXP has significantly lower speed performance, orders of magnitude less cycling endurance, and meanwhile is only about 50% cheaper than DRAM on today's market. So in spite of the fact that NVM has been widely portrayed as the only hope to tackle the memory war challenge, My research advocates a DRAM-only paradigm to innovate and improve future memory systems. This is motivated by three aspects. First, history clearly shows that any memory technology will undergo a very long maturity cycle. At this moment, there are still considerable uncertainties about NVM scalability and the impact of technology scaling on speed, cost, and cycling endurance. Therefore, as the industry continues to research new NVM, we should more seriously ask the question whether we have already exploited the full potential of DRAM. Second, the NVM cost advantage over DRAM has been very much overestimated. All the claims on the NVM cost advantage conveniently use today's bad accessible DRAM as a baseline, which unfortunately can be misleading. Any memory technology is fundamentally subject to a raw reliability versus cost trade-off. So today's DRAM either doesn't need ECC or just use very weak 8-byte ECC. In comparison, Intel 3D-XP Optane DIMM uses a much stronger 256-byte ECC. So with weak ECC, with weak ECC, DRAM must have very high raw reliability and hence high cost, and meanwhile achieve low latency. On the other hand, with strong ECC, Intel 3D-XP has low raw reliability and hence very low cost, and meanwhile suffer from long latency. However, it is really not fair to claim cost advantage of Intel 3D-XP DIMM by directly comparing with today's DRAM. Third, computing industry has been actively developing ecosystems to support medium agnostic, latency oblivious CPU memory interface, such as OpenCPI, CXL, and GZ. They enable CPU's connection to different memory media with variable data access latency. The above three facts motivate my research focus on DRAM-only heterogeneous memory hierarchy, as shown here. The computing system employs a heterogeneous DRAM fabric that consists of convenient but expensive but accessible DRAM, and low-cost block-protected DRAM that uses strong ECC to enable significant cost reduction. Due to the use of strong ECC, block-protected DRAM may have variable and non-deterministic data access latency. So compared with hoping for new NVM technology to mature, this DRAM-only memory hierarchy has several advantages as listed here. So the use of block-protected DRAM can largely reduce the overall memory cost. It can retain the true DRAM-grade speed and endurance based on existing DRAM technology. It has zero technology-level uncertainty and readily leverages the mature DRAM manufacturing infrastructure. So this thesis will study the implementation and utilization of heterogeneous DRAM-only memory systems for database systems cohesively across the hardware and software domains. At the hardware level, we will develop ECC and compression-centric design technologies and investigate the practical implementation of block-protected DRAM controller. We will further implement an FPGA-based OpenAPI compliant experimental hardware platform to prototype the develop the hardware-level design techniques. And at the software level, we will study how existing relational database and NoSQL database can effectively utilize the low-cost heterogeneous DRAM-only memory system. Moreover, we will develop a new in-memory key value store that can fully take advantage of the heterogeneous DRAM-only memory system. So at the first step, we will develop a DRAM-only heterogeneous tiered caching design approach for relational database. For relational database, to benefit from the DRAM-only heterogeneous memory, the easiest option is to use a block-protected DRAM as a second tiered cache, which together with database private cache form a transparent tiered caching system. In this way, we don't need to change any line of the code of the relational database. However, since the second tiered cache can only hold clean database pages, the system will subject to a high write I/O traffic, which can lead to a lower database performance. To leverage the block-protected DRAM to reduce the write I/O traffic, we propose a coordinated tiered caching approach, as shown here. By slightly changing the database source code regarding data page flush, we enable the block-protected DRAM tier to cache dirty pages. This can directly reduce the write I/O traffic, leading to a better database performance. So we have successfully demonstrated the effectiveness of this approach by modifying the source code MySQL. We carry out this bench workloads as shown here. And in this picture, A is a normalized TPS performance and B is a normalized write throughput. So the results show that the proposed coordinated tiered caching over the DRAM-only heterogeneous memory fabric can achieve noticeable performance benefit, especially for write-intensive workloads. We continue to explore this new research territory and hope we will have more results to report soon. So this ends my talk. Thank you very much.
Okay, thank you. Are there any questions by the audience? By the way, folks can also ask questions on the chat. So we can have more questions over there. Are there any questions? If not, then we can actually move on to the next talk. So the next talk is by Botu Peng from Paris Descartes University. And the title of the talk is Data Series Indexing Gone Parallel.
Everyone, my name is Badao Peng. I'm a PhD student at the University of Paris. I'm supervised by Themis Palpanas and Panagiota Faturu. Today I will present the work of my thesis, Data Series Indexing Gone Parallel. A data series is a sequence of data points ordered along some dimension, that is, the x-axis. If this dimension is time, we talk about time series, but in general it can also be position, as is the case of genome sequences, or angle for radial profiles of stars, or mass for mass spectroscopy, etc. Data series exist in virtually every scientific, and social domain, for example, in earthquake measurements in seismology, stock quotes in finance, and electroencephalograms in medicine. Once we have such data series collections, we want to analyze them, in order to extract useful knowledge. Examples of data series analysis algorithms include classification, clustering, outlier detection, and identification of frequent patterns. We observe that all these algorithms depend on similarity search. In the context of data series, similarity search refers to the following problem. We have a collection of series, and a query series, then, we want to identify the series from the collection that have the smallest distance to the query series. There are several different distance measures that have been proposed in the literature, but by far the two most popular are Euclidean distance, and dynamic time warping distance. Our proposed approaches support both these two distance measures. Since similarity search is used by all these analysis algorithms, speeding up similarity search translates to faster execution times for the analysis algorithms, as well. However, data series similarity search is a hard problem, for two reasons. First, because data series are high-dimensional objects. In this case, dimensionality refers to the length of the series, that is, the number of points. Typically, series have dimensionalities between a few hundred and a few thousand. Note that even when we deal with streaming, or infinite series, the patterns of interest have lengths in the order of hundreds to thousands, so we process subsequences of that dimensionality. Second, data series collections have very large sizes, with several collections across different domains having sizes in the order of multiple terabytes. Therefore, we need techniques that will allow us to answer similarity queries fast for very large datasets, and this is exactly what data series indexes can do. Nevertheless, even the current state-of-the-art index, developed in our previous work, takes a long 3.5 minutes to answer a nearest neighbor query on a 256 GB dataset. In our work, we focus on the use of modern hardware to accelerate data series indexing and similarity search. In particular, we have developed the following techniques. First, Paris, a parallel data series index designed for multi-core architectures and disk-resident data. We describe parallel algorithms for index creation and exact query answering, which employ parallelism in reading the data from disk and processing them in the CPU. Second, MESSI, a parallel in-memory data series index. Contrary to Paris, MESSI employs a tree-based query answering strategy that minimizes the number of distance calculations, leading to highly efficient similarity searches. Last, PAR-GIS, a GPU-based data series index, which we are currently developing. Paris Index. We will start by presenting Paris, which is the first data series index designed for modern hardware. Paris exploits multi-core, multi-socket, and single-instruction multiple data architectures in order to speed up both index creation and query answering. As a result, Paris achieves perfect overlap between the disk I/O and the CPU costs, completely masking out CPU cost. When creating the index, Paris query answering is 1 to 3 orders of magnitude faster than previous approaches. Let's see how exact query answering works in Paris. When a query arrives, we run an approximate search, which means we go down the index tree to the most promising leaf. We examine all the series in this leaf, by computing the real distance between the query and the raw data series. And we select as the current best so far answer the one that minimizes the distance to the query. Note that another leaf may still contain a series with an even smaller distance to the query. Then, the main thread creates several lower bound distance calculation workers to calculate the lower bound distances, and to insert the lower bounds, whose values are smaller than the best so far, into the candidate list array. After we compute the lower bounds, the main thread creates several real distance calculation workers, who repeatedly read entries from the candidate list array in an atomic way. For each entry, they retrieve the corresponding raw data series from the file on disk, calculate the real distance to the query, and if necessary, update the shared best so far variable. Finally, we emit the nearest neighbor answer. MESSI index. We observe that data analytics algorithms often operate on subsets of the entire data series collection, which fit in memory. To perform complex analytics operations fast, we thus require to build efficient in-memory data series indices. This is the contribution of this paper. More specifically, we present MESSI, the first in-memory data series index which has been built upon and incorporates current state-of-the-art techniques in sequence indexing. MESSI exploits the computational power of multi-core and multi-sockets architectures, as well as single-instruction multiple data architectures, in order to achieve time-interactive exact query answering times at about 50 milliseconds. We achieved this by implementing a novel exact query answering algorithm which minimizes the number of required distance calculations. We also employed a parallel-friendly index framework with low synchronization cost when building the tree index. The collection of experiments we performed illustrate that MESSI is up to 11x times faster than previous state-of-the-art algorithms. We will discuss the MESSI query answering algorithm here. The first part, where we obtain the first best so far, is similar to Paris. Then, the workers do not produce a candidate list array. Instead, they start traversing the index tree subtrees, one after the other, using the best so far distance in order to decide which subtrees will be pruned. The leaves of the subtrees that cannot be pruned are placed into a fixed number of minimum priority queues, using the lower bound distance between the raw values of the query series and the ISAC summary of the leaf node, in order to be further examined. Each thread inserts elements in the priority queues in a round-robin fashion so that load balancing is achieved. This results in all queues containing about the same number of elements. As soon as the necessary elements have been placed in the priority queues, each index worker chooses a priority queue to work on, and repeatedly calls delete min on it to get a leaf node, on which it performs the following operations. It first checks whether the lower bound distance of the leaf node stored in the priority queue is larger than the current best so far. If it is, then the leaf node does not contain any series that can be part of the answer, and can be pruned. Otherwise, the worker needs to examine the series contained in the leaf node, by first computing lower bound distances using the ISAC summaries. For each data series whose lower bound distance is smaller than best so far, its real distance from the query series is computed, using the raw values. During this process, we may discover a series with a smaller distance to the query, in which case we also update the best so far. When a worker reaches a node whose distance is bigger than the best so far, it gives up this priority queue and starts working on another, because it is certain that all the other elements in the abandoned queue have an even higher distance to the query series, and therefore, will not contribute to the final answer. This process is repeated until all priority queues have been processed. During this process, the value of best so far is updated to always reflect the minimum distance seen so far. At the end of the calculation, the value of best so far is returned as the nearest neighbor answer. We ran experiments with synthetic datasets, as well as real datasets from neuroscience and seismology. We compared our algorithms, Paris and MESSI, to several baselines, including the optimized serial scan algorithm, and the state-of-the-art disk-based index, developed in our previous work. In the first set of experiments, we compare Paris to state-of-the-art disk-based index, ADS. For index creation, Paris is more than 2 times faster than ADS. For query answering, Paris is up to 5 times faster than ADS on hard disk drives, and up to 8 times faster on solid-state drives. Finally, Paris is more than 2 to 3 orders of magnitude faster than the serial scan method UCR suite. When compared to an in-memory version of Paris, MESSI creates an index up to 3.9 times faster. In query answering, MESSI is 80 times faster than a parallel in-memory version of UCR suite, and up to 11 times faster than the in-memory version of Paris. Remember that Paris was designed for disk-resident data. These results demonstrate that a straightforward in-memory index solution is suboptimal, and that the specific design choices we made for MESSI have a significant impact on its performance. To conclude, we observe that large data series collections exist in virtually every domain, and we need data series indexes to support fast similarity search. Our proposed approach, Paris, is the first parallel on disk data series index designed to take advantage of multi-core, multi-socket, and single-instruction multiple data architectures. MESSI is the first in-memory parallel data series index. Not only does the design of MESSI balance the workload among workers, but it also minimizes the synchronization cost. MESSI creates an index and answers queries more than one order of magnitude faster than previous approaches. This makes MESSI the first index that can answer similarity queries on 100 GB datasets in 50 milliseconds, that is, at interactive speeds. Thanks for listening. Any questions?
Yeah, thank you. Are there any questions by the audience? I had a quick question actually. So,
Yes.
so you try this out. So can this be extended to maybe approximate search, like approximate nearest neighbor search? So you're basically doing this for exact search, right? So can the
Yes.
techniques?
Yes, I think so. We can just stop when only process several nodes. So it can also be used for that if we have the time bound.
Okay, so have you tried comparing it with some approximate nearest search algorithms?
Not yet. I think it's the next step.
Yeah, makes sense.
So this is Themis Palpanas, who I'm the supervisor of Botao. So let me just add one more comment here. So there are several different flavors of approximate search. And one flavor that is approximate search with no guarantees whatsoever about the quality of the answers. This is readily supported by these indexes that we presented today. Now, there are also other flavors that provide either probabilistic or deterministic guarantees on the quality of the solutions. And these are extensions that we have shown in some other works of ours will be presented in that were presented in VLDB on how we can apply these extensions. And in those works, we also compare the performance of data series indexes with other approaches for approximate nearest neighbor search.
Got it. Yeah, makes sense. I was actually referring to the ones that have either, as you said, probabilistic or deterministic guarantees in terms of approximation, right? And that's great to hear. Yeah, thank you.
Yeah, so please take a look at the paper Lerny and Hydra that will be presented in VLDB this year. So this is a comparative evaluation for approximate nearest neighbor of different techniques. And there we basically show that, for example, for techniques that do provide probabilistic guarantees, so this will include, for example, LSH-based techniques. The performance of the data series indexes is much better. So we can provide answers faster and more accurate than what LSH does. And especially if we want to do this for disk-based data, then the data series techniques are the only viable solution.
Got it. Yeah, thank you so much, Themis. This was great. Thank you. Okay, so if there are no other questions, we can move on to the next presentation. So the next presentation is by Yang Li from the China University of Geosciences, and the topic is area queries based on Voronoi diagrams.
Good afternoon, everyone. I'm the speaker Yang Li. I'm from China University of Geosciences. The title of my presentation today is Area Queries based on Voronoi diagrams. My presentation is divided into 5 parts: introduction, preliminaries, methodologies, experiments, and conclusions. Part 1, Introduction. Area query is to find all the points that lie in a given area from a certain set of points. As a basic spatial query, is widely used in many fields such as aerospace, military, physics, urban planning, transportation planning, and so on. Like other spatial queries, the area query is not only compute-intensive but also I/O-intensive. A number of methods have been proposed to implement this query. One of the best known is to get a rough candidate set through a special index, and then refine the candidates through geometric validations to get the final result. As shown in Fig A, the process of the traditional one consists of two phases, filtering and refining. The first phase doesn't require loading the full geometric information or performing expensive geometric calculations. However, the majority of points that don't meet the query condition can be pruned. The second phase only requires further refinement of the results from the previous step. It's usually more time-consuming than the first phase. For the traditional approach, the spatial index must support window query. The candidate set contains all the points in the MBR of the query area. If the shape of the query area is very similar to a rectangle, the result set will be very close to the candidate set in size. However, in practice, the shape of the query area given by users is often an irregular polygon. In this case, the size of the candidate set is often much larger than that of the result set. If the number of the candidates can be reduced, then the time cost of the refinement will be saved. Therefore, we propose a novel area query approach based on Voronoi diagrams as shown in Fig B. The candidate set is not obtained directly by window query, but by an incremental algorithm based on Voronoi diagrams. This is the comparison of the number of accessed points. Besides the points lie inside the query area, the candidate set only contains a small number of points lying close to the boundary of the query area. It can be seen from the figure. The candidate set of our method is generally much smaller than that obtained by window queries. Hence, the proposed method performs more efficiently than the traditional one. Part 2. Preliminaries. In this section, I will introduce the concepts of Voronoi diagram and the Delaunay graph to enhance the understanding of our methodologies. The definition of them are shown in this page. It can be seen that the Voronoi diagram and the Delaunay graph are unique and they are due each other. The Delaunay graph must be a connected graph. Part 3. Methodologies. In this section, I will describe the implementation and mechanism of the proposed algorithm in detail. First, let's do a classification of the points in the database. Given a query area A and a set P of points, the points in P can be divided into three types. The black points represent the points lie inside A. We call them internal points. The gray points represent the points in P that lie in A and not adjacent to the boundary of A. We call them external points. The green points lie in A and not adjacent to the boundary. They are referred to boundary points. From the Delaunay graph of these points, we can get three important properties, as shown below. According to these three properties, we can further conclude that an internal point cannot be adjacent to any external point. In the Delaunay graph, between two internal points, there must be at least one connection path that goes through the internal or boundary point. Therefore, we can start at any internal or boundary point and access all the internal and boundary points one by one, without passing through any external point. Based on this idea, I propose a Voronoi diagram-based algorithm for area query. Its pseudocode is shown on the right. Part 4. Experiments. In order to evaluate the performance of our method, we conduct a number of experiments with the traditional method based on R-tree as a comparison method. Our experiments are designed into two sets. The first set is used to evaluate the effect of data size on the performance of the algorithms. The query size is fixed at 1%. As the data size changes from 100,000 to 1 million, the time cost varies from 10% to 31%. The number of candidates saved by our method compared to the traditional one varies from 35% to 43%. The second set is used to evaluate effect of query size on the performance of the algorithms. The data size of the set is fixed at 100,000. As the query size changes from 1% to 32%, the time cost varies from 12% to 38%. The number of candidates saved by our method varies from 35% to 45%. Part 5. Conclusions. We are the first to apply Voronoi diagrams in spatial area queries. Because the candidate set is greatly reduced, the proposed area query method performs less spatial calculation than the traditional one. Therefore, the query efficiency of our approach is much higher in the vast majority of cases. Our work greatly expands the application of Voronoi diagram and improves the efficiency of area query. It's of great significance for the future research. Thank you.
Okay, thank you. Are there any questions by the audience? Okay, so if there are no questions, then we can move on to the next presentation. So the next presentation is the final presentation of this session. And the presentation is by Wenxiu Fu from York University. And the topic is Picube for fast exploration of large data sets.
Hi everyone. Today my presentation is Picube for fast exploration of large datasets. A Picube is a hierarchical data structure. My motivation to create Picube is to support like realization, data mining, or some potential analysis of large datasets. Hierarchical aggregation is a preferred choice without powerful clusters or for online computation or enough information to predict and prefetch queries. Hierarchically aggregating data in advance can support users to traverse through different levels of details to analyze the data efficiently. There are two representative kinds of methods. One is based on DataCube, which aggregate across every possible set of dimensions of a dataset. The other is based on the aggregate pyramid, a form of research from our lab, which aggregate all dimensions in concert. Unfortunately, those methods have their limitations for supporting some specific exploration. For example, supporting exploration of OD datasets. Let's consider the New York taxi dataset. It's a 5-dimension OD dataset where the first 2 dimensions represent a pickup location and the following 2 dimensions represent a drop-off location, and then the last one represents the temporal dimension. Given this dataset, a DataCube approaches can result in extremely large cubic data structure and aggregate more than is needed. Like according to X summarizing Y is wasteful as 2 of them together is defined in one location. A cuboid over X and U is meaningless as they doesn't make sense together. So although decomposing this full cube into a collection of subcubes may decrease the size, but it doesn't work for the OD dataset because it may break the connections between the dimensions and lose the chance of cross-layer optimization. In this scenario, an aggregate pyramid is equally not helpful as aggregating this 5 dimensions together doesn't offer the necessary flexibility for dimension-wise roll-ups and drill-downs. Although the aggregate pyramid is well-behaved in size, but it's meaningless without our needed flexibility. So now, I want to strike a balance between these 2 kinds of approaches. Design a hierarchical data structure that is flexible enough for different exploration scenarios with reasonable size and low-cost construction. That is Picube. If we see that DataCube and the pyramid represent 2 extremes of aggregation, we want our Picube bridge this spectrum between them, allowing us to specify the required aggregate. Then, what is a Picube? Picube is defined as a partitioned, inductively aggregated qubit data structure. In Picube, dimensions of the dataset are partitioned into axes. Within each axis, all the dimensions are aggregated in concert as with an aggregate pyramid. And then when inductively aggregate over every possible set of axes, result in a cube data structure. How do we build a Picube? We continue with the same example scenario, the New York taxi dataset. We assume the exploration scenario is to get the distribution of the drop-offs of a given pickup range with a given interval at time. Then we can build a Picube with count as the aggregate function. The first step to build a Picube is partition. We partition the 5 dimension into 3 axes according to their semantic meaning. Then we bin each dimension into 4 bins. After binning, we created a 5-dimension graded space with a 2D UV grid. Then in each grid cell is a 3D grid for X, Y, and T. Then the data mapping into this graded space form a stratum, which we call the base. Now we can start our aggregation. So a non-overlapping sliding window is performed with our aggregate function to aggregate values of cells within this window's bins into one corresponding supercell. The base is where we start with the aggregation, so we can tell it's with the highest resolution of the data, which means the data aggregate the least. So let's do this, the interactive aggregation step by step. We set a window size with 2 cells for X, Y, 1 for other dimension. With this window, when we aggregate over the base, see S0, resulting in a stratum, see S1. Then we take S1 as a base, use the same window aggregating over S1, resulting in S2. The aggregation now rolls up along axis AXY with 3 resolutions. And now we get our y-axis Picube. We can tell from the structure that this is actually a pyramid along axis A and AY, axis X and Y. So the pyramid, in fact, is a single axis Picube. Now, we take each stratum from the pyramid, from the result, former result as a base, with these blue windows aggregate along axis T. The aggregation results in a 2-axis Picube with 9 strata. There are also 3 resolutions along axis T. So now we need to extend the label of each stratum to 2 coordinates to locate each stratum. Taking the result stratum from the former aggregation as the base, performing with this green window, the aggregation can roll up along axis UV, and the result in 27 strata. Now we need 3 coordinates to label each stratum. After this, the aggregation is done. From the aggregation process, we can tell that the aggregation over S1, 0, 0 along axis XY aggregate to S2, 0, 0. We then say S2, 0, 0 is dependent on S1, 0, 0. So we can tell that the coordinates reflect their dependence relations. At the same time, the dependence relations will determine the coordinates of each stratum. So with strata, the coordinate system, the dependence relation, we got a stratum space. With all those together, we got a Picube. The definition of a Picube and the way to build it seems naive, but when we look deep into the Picube, we can see more challenges. We build a Picube by merging cells stratum by stratum. When data is dense, we merge several non-empty cells to one supercell, then the size of each stratum will decrease quickly, and the size of the Picube thus is well behaved. However, when the dataset is sparse, it's different. We may only aggregate only one non-empty cell to a supercell. In other words, we're duplicating this data to next stratum. Then we might do this a lot. The size of such a Picube can be intractable. According to this observation, we name those cells that aggregate nothing but themselves as islands. Then it comes our first challenge: constrain replicates of each island. When number of duplicates of each island stored in the Picube is well constrained, we call it concise. From the picture, we can tell cells 40 and 43 from this stratum aggregate to cells 10 of S2. The cells 10 of S2 is an island which is equals to cells 2 of S3. This is where it touches with other cells and turn to be a non-island. What if we can skip this step and aggregate from 40, 43 from S1 to cell 2 of S3? It's acting like we're pushing cell 10 of S2 to cell 2 of S3. We call this process pushing the island to where it touches. Pushing the island will leave a hole at where it should be. So after pushing all the island, we can see that the structure being like this and with a lot of holes at different places. The key point in pushing an island is to find the correct strata where it touches. It's quite simple in a single access Picube with a linear dependency relation, because there's only one stratum higher meets the requirement. When Picube is multi-access, it becomes complicated. You may find numbers of strata meet the requirement. So where should we push the island to? In other words, how many of those should we materialize? So recognizing island, pushing the island, and decide how many replicates of the island need to be materialized consists of our first challenge. In the former example, we first aggregate along axis XY and then aggregate along axis T. Is this the only way to do the aggregation? Apparently not. We can always aggregate along X, Y, and T together, and at this step, aggregate along axis XY, and then along XT here. In a two-axis Picube, there are 16 materialized ways. We call the order to materialize the strata as materialization paths. Among these 16 passes, which one is the most efficient one? So without the pushing island, a cost model for calculated materialization path is simple. We can make just only consider cardinality and parallel computation. However, in a concise Picube, we need to consider the mutual influence between pushing islands and choosing the materialization path. Example, if we push in an island from S00 to S02, leave a hole as S01, then we may not aggregate from S01 to S11 because a hole may cause aggregation mistake. So our second challenge is how to determine a materialization path in concise Picube. The last challenge is about how to query from Picube. We now one-dimension querying the cells in single-axis Picube, but when the Picube is multiple axis, we need to find a way to design the index to support the range query efficiently. We also need to find out how to fill in the rows when fetching from such a concise Picube. So in the end, Picube is designed to be a flexible hierarchical data structure that can be built efficiently in a reasonable in size, no matter the dataset is dense or sparse. a Picube can be very useful in the way like realization or improving some traditional clustering algorithms like k-means. And also, I believe the application of Picube are with great potential. Thank you.
Okay, thank you very much, Wenxiu. So are there any questions by the audience? If not, then I think we can end the session here. So thank you again for participating. Thank you, speakers, for presenting. It was a great set of talks. And yeah, do enjoy the rest of the conference. So I think that's the session here officially ends.